All right, so to make sure this makes sense, let's walk through an example. I'll take you all the way through how to run a regression in Excel. We're going to be working with the data from table 5.3 in your textbook. Now, so we're going to want to be able to recreate this for the problem set. So I'll walk you through everything, starting with going through what the data is, all the way up through trying to interpret the results. So first thing we want to do is install the multivariate regression app in Excel. So to do that, go over here to File, and I have to go under More. You might not have to, but you want to click on the Options tab. Under the Options, look on the left here for Add-ins. Click on that, and then click on the Analysis Tool Pack. That's the Excel add-in we want to use. Now, the first time I did this, I just clicked OK and thought that was it, that would add it, but it turned out that did not add it in. The first thing you want to do is go to Manage here, click Go, and then check the Analysis Tool Pack. So that way it's uploaded and it's on your menu banner at the top. Then we can hit OK. Now, if we go up here, go under the Data tab, right here under the Analysis, the Data Analysis option, that's what we just added. Now, before we go through that, let's look at the data that we have and try to describe it. So this data right here is, it's a cross-section data. So we have 30 schools here. The first variable, college, they're numbered 1 through 30. So this is a snapshot in time looking at 30 different colleges. And it contains 6 variables. The Q slices, that's our variable of interest, and the other 5 are going to be our independent variables, or the ones we're looking at in our model to estimate the quantity of slices. So the quantity of slices, this number here is for the first college, 9.89. That's the average quantity of slices bought by students per month. The P slices, that is the average price of slices in cents. So this 97.3, it's not $97.30, it's 97 cents on average. The tuition for the first one is 17.92. That's the tuition in thousands of dollars. So for that first school, it's $17,000. The P soda or P soft drink in your book is the average price of soft drink, again, in cents instead of in dollars. And then we have dummy variables for whether the school is urban versus suburban and residential versus commuter. Now, our regression is going to be represented by the equation that you see here in about the middle of the screen. So we're trying to estimate the quantity of slices. So that's going to be our dependent variable. We call it dependent variable because it's the one that's being estimated, and the number that that we get from the equation is dependent on the other variables in the equation, the right-hand side variables. On the right-hand side, we have A, which represents the constant value. So if we have zeros for all the other variables, that's how many slices would be sold. So we have B1 times PS, so that PS stands for the price of slices. Then B1 is our first coefficient. So that's what we're trying to estimate is the B1. We have that plus B2, our second coefficient, times the tuition, plus B3, our third coefficient, times the price of soda, here represented as PD. B4, our fourth coefficient, times U, the dummy variable representing urban, plus B5, our fifth coefficient, times R, the residential dummy variable. So now in order to run this regression, we're going to go to the Data tab. So typically we're at home here. Let's go over to Data and click on the Data Analysis. And we're going to go to the group labeled Analysis. Click on Data Analysis. Then we're going to click on Regression. So scroll down here to Regression and then click OK. First, they're going to ask you a few things. So here, input the Y range. I'll click on this little thing to pull up the box. And then we're going to select the data for Q slices, our dependent variable. And then click that back down when you've got all the data in there. Now we're going to input the X range. That's going to include all the right-hand side or our independent variables. We go from P slices all the way over to residential, and then down to the bottom of our data, or number, oops. There we go, all the way up. Make sure we get all 5 of those. I'm going to click this little box here to show that we have labels, because the top of that included the labels. I think that makes the output easier to read. You could opt to not include that first row, which is just the data labels, and then you would leave that just not checked. Then we want to select our output range. That's going to determine where the table is going to go, whether it's going to be on this Excel sheet or it's going to put another one. Here we're going to select a new worksheet ply. That way it's we don't have to worry about having the results be put over like data we already have on this window. I think that just makes it easier. And then for what we're doing right now, that's all we need to select, and then hit OK. And this, it brings up another sheet 2, and of course we can expand some of these out so it's easier to read them. Now I've included a link to a website with these directions of the model. It just walks you through it written out in case you're having trouble following this or you need to look through and just see it done another way. So now, what will we expect? The book lists 5 hypotheses. I think it's worth talking about. The first, what they expect to happen is that the price of pizza is an inverse determinant of the quantity of pizza. So the sign of the coefficient is expected to be negative. The higher the price, the less people are going to want to buy. That's the first law of demand. That should make sense to us because we're all consumers. For the second hypothesis, so if tuition is a proxy for income, which was our goal, pizza could either be a normal or an inferior good. So we can't say beforehand, or we'll struggle beforehand to know whether there's an inverse or a direct determinant. So if the sign is going to be positive or negative. The third hypothesis for our third variable, the price of soft drink, we think it's going to be an inverse determinant of the demand for pizza. So we should expect the sign of the coefficient to be negative. Again, because these are complementary goods. So if the price of soda goes up, we'll expect people to buy less pizza because they tend to buy those two goods together. Our fourth hypothesis for our fourth variable is that location in an urban setting is expected to be an inverse determinant with demand for pizza. And finally, the hypothesis 5, pizza demand is expected to be lower at residential colleges than for non-residential colleges. So now let's see how these hold up. Let's look at our results. So what we want to focus on first is at the bottom. So we'll check the coefficient size and magnitude. So here at B16, the coefficient underneath there. So for our intercept, we have 29. So basically, if everything was 0, we would expect consumers to buy 30 slices of pizza. Now, the price isn't ever going to be 0. Tuition isn't ever going to be 0. I guess unless you have, well, no, it doesn't even count what you pay. In this case, it's going to be the sticker price. So even if you have scholarships, it wouldn't be 0. Price of soda wouldn't be 0. So we could say that in this case, the coefficient doesn't matter. The constant doesn't matter. It's not a situation that would ever occur in real life. But sometimes that is, so it's something that we check. So the price of slices is negative 0.09. So there's that inverse relationship which we expected. Now we have a positive relationship with tuition, and it's 0.05. Price of soda is negative 0.081. And again, that's what we expected because they're complementary goods. And then for urban and residential, for urban, we have negative 0.74. And for residential, we have negative 3.0. So residential has a much stronger impact on the quantity of pizza demanded by consumers, much stronger than any of the other variables. All right, so for the calculating the elasticity, we're going to do that. I'll include that later on a PowerPoint slide, so that way we can see all the numbers we're working with. It'll be too difficult to do it with this Excel sheet up. So let's move on to determining the statistical significance. So we've estimated these coefficients. can we be certain or relatively certain that they're actually accurate? So how we do that is we look at first the t-statistic and then the p-value. Now, the t-statistic and the p-value show basically the same thing. Your textbook walks you through how to calculate the t-statistic. We don't have to here because it's shown for us, just like it shows the p-value for us. But to calculate the t-statistic, what you have to do is divide the coefficient by the standard error, and that's your answer. It's that simple. Now, if your t-statistic is above 2, then we consider that statistically significant. Now, why we do that? Typically in economics, we choose the 5% level of significance. What the 5% level of significance means is that we're 95% certain that the estimated coefficient is representative of the population. Basically, we're 95% sure that we're correct and that the coefficient we calculated wasn't due to random chance. So if the t-statistic is greater than 2.065, then it's statistically significant, or it's greater than 95%. Ideally, we'd like to get that even higher. We'd like to get that to the 1% level of significance. So we're 99% certain that the coefficient that we estimated in the model is representative of the population. Now, besides looking at the t-statistic, we can also look at the p-value to see if it's statistically significant. The p-value is going, rather than looking to see if it's greater than the number 2, we want it to be as small as possible. So if we want it to be significant at the 5% level of significance, we want the p-value to be 0.05. If we want it at the 1% level of significance, we want it to be 0.01. So basically, what the p-value is the percentage. So for instance, let's look here. We have, for the intercept, the t-statistic is 13.24935, greater than 2. The p-value here is incredibly small. It's 1.56 times 10 to the negative 12. Very, very, very small. Let's look at the price. The coefficient is negative 0.09. Our t-statistic is negative 7. So again, much greater than 2. And here we have this very, very small 4.635, on repeating, times 10 to the negative 8th. Now tuition, the t-statistic here is 1.73, so not quite 2. So we're not significant at the 5% level. Our p-value here is 0.0963. So we're at about 9%, 9.6%. So below the 5% level of significance. So let's see, which ones are significant? Right here we have the intercept, the p-value extremely small. That's statistically significant. P-slices, again, that's significant. This one is not significant at the 5% level. If we didn't care as much about accuracy and we wanted it to be at the 10% level of significance, so we're 90% certain that the estimated coefficient is representative of the population, this would be statistically significant, just barely. It's just under 0.1. Right here, the price of soda, the t-statistic is negative 6, which again is greater than 2. And the p-value is 1.47 times 10 to the negative 6th. So it's very, very small. This is also statistically significant. Urban, this variable, we have the coefficient of negative 0.74. The t-statistic is 1.2, and the p-value is 0.2. 1.2 is less than 2, so that would suggest it's not significant, and we see the p-value is extremely high. It's at 20%. We want it down at 5%. And then finally, residential. The stat is negative 6. So again, that's greater than 2, larger than 2. And then the p-value is 2.14 times 10 to the negative 6th. So extremely, extremely small. Much lower than 0.05 or 0.01. So it's statistically significant. Now, there are two more tests that we should be concerned about here. That is the R-squared and the F-stat. So up here at the top, this gives you the R-squared, the adjusted R-squared. We're just going to be concerned about the R-squared for this class. The R-squared is a number between 0 and 1. What the R-squared tells you is how much of the variation in Y, so in this case, the quantity of slices that are demanded, how much that can be determined from the variables in the model. So if your R-squared is 0, that means none of your dependent variable, none of the quantity of slices that are demanded can be explained by your model. In other words, you have a really, really bad model. You almost have to try to get it to be a 0. 1 is perfect, that all the variation in your dependent variable, so the quantity of slices that are sold in this case, are going to be explained by your model. That's basically impossible to hit unless the quantity of slices that are sold is your independent variable and dependent variable. That's basically the only way. But we can get extremely close. The higher your number is, the better. So here, look what we have. Our R-squared is equal to 0.88. 0.88 is pretty close to 1. So we say 88%, a little bit over 88% of the variation in the quantity of slices of pizza that college students demand can be explained by our model. So this is a really good model. The other thing we want to look at is the F-test. Now, this is a test of joint significance. So our t-stat and our p-value down here, these show the statistical significance of each of the coefficients. What our f-stat does is show the statistical significance of all of the variables in our model. So if our entire model is statistically significant, we can say we have a good model. If it's not statistically significant, that means we need to go back to the drawing board. We're probably missing some variables. We need to reconsider. Maybe some of these variables, it turns out, doesn't matter for our dependent variable. We can think of the F-test as the statistical significance of R-squared. Now, you don't have to worry about calculating these. There is some stuff in your text about like how to do that by hand. Well, maybe that's just in the appendix on the actual chapter. But because it spits out the number for us, we don't have to worry about it. So we want the test to be at the 95% level as well, just like we wanted for each of the individual variables. Here, that means below 0.05. The smaller, the better. So here's our F-stat, which is basically like our T-stat. So that's going to be, like a whole number. And we want it to be, I believe, greater than 2.065. We can look at this here, significance F, or the p-value of the F-stat. It's called both of those. I typically call it p-value of the F-stat. We want this below 0.05. This is just like what we want for the p-values. And we see right here, it's 1.71 times 10 to the negative 10th. So extremely, extremely small. This is exactly what we want if our model is accurate. So we can say that our model captures a lot of what determines the quantity demanded for slices of pizza. 88% of the changes is captured by our model. And we could say that the variables we selected do a good job of this. We could say that all of them are worth including in our model. Despite the fact that some of these might not be statistically significant, we find our overall model does have statistical significance. So we can be confident using this model to estimate the quantity demanded of pizza.